Welcome again to this topic, electrostatics. We are in lesson 5 and we are emphasizing about electric potential, and we are mostly going to do numerical calculations. The first example says that a plus or a positive 4.5 microcoulomb charge is 23 centimeters to the right of a negative 8.2 microcoulomb charge. At the midpoint between the two charges, what is? So we want to find the electric potential in the midpoint of the two charges. The diagram that we see here is the illustration diagram on the left, illustration for the question. So the two are separated by 23 centimeters, and then they are saying that the positive 4.5 microcoulomb is on the right. So it's on the right of a negative 8.2 microcoulomb. And then the question is, what's the electric potential midway between? So if it's midway between, it means that it is 11.5 centimeters on either charge, as it is indicated. And we know that electric potential is Q over R. So the electric potential at this point is going to be the electric potential at O is due to the charge placed at A, and again is due to the charge placed at B. Therefore, we would say that potential at O is equal to potential at O due to A plus potential at O due to B. So the potential at O now is going to be, if we substitute in, it's going to be 9 times 10 to the power 9 times the charge placed at A, which is negative 8.2 times 10 to the power negative 6 divided by the distance between A and O, which is going to be 11.5 times 10 to the power negative 2, then plus the potential at O due to B, which is 9 times 10 to the power 9 times the charge at B, which is positive 4.5 times 10 to the power negative 6, the whole of this divided by 11.5 times 10 to the power negative 2. Therefore, V at O, if you add these two, is going to give us a negative 2.89 times 10 to the power 5 times 10 to the power 5 volts. So electric potential is a scalar quantity, and then when we are calculating electric potential, we include the negative on the charge. If we go to part B of this question, we want to find the electric field at O, electric field at O. The diagram on the right is the same illustration, but this time we are finding the electric field, which is the same as electric field intensity. So we remember that electric field intensity is denoted with E, and that's equal to Q over R squared. This is the same as the electric field intensity due to a point charge, at a certain distance from that charge. So the electric field intensity at O is due to the charge placed at A and also due to the charge placed at B. Electric field intensity is a vector quantity, therefore we are interested in the magnitude and direction. So since the one at O is due to the two charges, we shall say we have to get the E at O due to A, which is going to be 9 times 10 to the power 9, that constant K, times the charge placed at A, which is given in the question as 8.2 times 10 to the power negative 6. Be careful, we take the magnitude when we are calculating electric field intensity, divide by the distance, which is 11.5 times 10 to the power negative 2, but this time squared. And this is going to give us 5.58 times 10 to the power 6 volts per meter. So where is that? What is the direction of E? So the direction of E due to this charge, we have already seen from the previous question that this is a negative charge here. If it's negative, it means that the electric field intensity at O due to that charge will follow the electric field lines due to that charge. The electric field lines of a negative charge are always into a negative charge. So that means this is going to be to the left. With that arrow going to the left, or you would say the word left. Well, we go on. As we mentioned earlier, we said that the electric field intensity at O is due to B also, so that's going to be E at O due to B. If we substitute, we get 9 times 10 to the power 9. From the formula, that's K times the charge placed at B, which is positive 4.5 times 10 to power negative 6. That's a micro, divided by the distance of B from O, which is also 11.5 times 10 to the power negative 2, but this is squared. If we feed in the calculator, we are going to get 3.06 times 10 to the power 6 volts per meter. So it is that answer. Now let's see the direction, because we said E is a vector quantity. That's the magnitude. Let's see where it is going. So come back to point B. Point B, we have seen that there is a positive charge according to the question. There is a positive charge. So if it is positive, then what is the direction of electric field lines due to a positive charge? Of course, the electric field lines due to a positive charge are out of the positive charge. Therefore, that's the same direction for E at O due to B. Remember, this was E at O due to A. So that's the field lines are out of a positive charge at B. Therefore, this field is to the left. So you can put the arrow towards the left. That's the direction of EOB. So since now EOA and EOB are all to the left, therefore the resultant E at O is going to be the summation of E at O due to A plus the E at O due to B. And if you add these two values that we have got, you're going to find that in your calculator, carefully dialed, you get 8.64 times 10 to the power 6 volts per meter. This is the magnitude. Again, we need the direction. Therefore, since all of them were to the left, it means that obviously the resultant is also going to be to the left. Next example. It reads, the demonstration of Van der Graaf generator has a 25.0 centimeter diameter of a metal sphere that produces a voltage of 1000 kilovolts near its surface. What excess charge resides on the surface of the sphere? Okay, this diagram here that we see is the illustration of a Van der Graaf generator. The Van der Graaf generator is used to produce electricity by action at points. So we have sharp points, and then the belt is rotating, and then charges are accumulating on the surface. We shall not go into details of that, but this diagram shows that charges, the positive charges, have already accumulated on this surface of this sphere. But what we are interested in is to calculate the excess charge that resides on the surface of the sphere. We needed to know the diagram because if you look at this diagram, there's a small part inside it, and that distance is the radius of the sphere. So you can see that in the question we are given diameter, therefore, and yet we are interested in the electric potential V, which is equal to KQ over R. KQ over R, and R here is going to be the radius of the sphere because the charge is placed in the center of the sphere, and it's a distance R, which is the radius from the surface. It's similar to having a charge Q somewhere here, and then you want to find the electric potential at a distance R, maybe electric potential at P, the distance R from the charge. It's the same way, so that's the way it is. Okay. Then here we shall see that V is equal to, here we have the formula already. Now we are interested in the excess charge. Therefore, in this case, the formula is going to be equal to V times the radius of a sphere over K. So the charge is going to be V given as 1000, but it is kilo, so that's times 10 to the power 3, multiplied by the radius of this sphere. So radius of a sphere, since the diameter is 25 centimeters, radius would be equal to 12.5. Yes, 12.5, but it is in centimeters, so that's power negative 2, divided by K, where K is known as 9.0 times 10 to the power 9. If we feed in our calculator, we shall end up getting 1.39 times 10 to the power negative 5 coulombs. Well, you can change this to microcoulombs or nanocoulombs, whatever you wish, but that's the answer. The next question says that what magnitude of potential difference is needed to give a helium nucleus bracket of charge 2e close bracket 65.0 kilo electron volt of kinetic energy? This is good because we know that electric field is an accelerating field. When we place a charged particle in an electric field of a certain potential, then that particle can be accelerated, can gain velocity. So now we want to find the electric potential difference that is needed to accelerate a charge, a particle which is a helium nucleus having a charge of 2e. E here represents the electronic charge, which we know very well. Here we need to know that if the particle was at rest, then it at rest initially in the electric field, then it has electric potential energy, and if a potential accelerates it to a certain velocity, it means that electric potential energy has been converted into kinetic energy. That's conservation of energy. So here you have that electric potential energy is going to be equal to 1/2 mu squared, will equal to the kinetic energy that is going to be gained. And we have the kinetic energy in electron volts as 65.0 kilo, so that's times 10 to the power 3 electron volts. We know that, we recall that electric potential energy of a charge or charged particle is equal to the charge multiplied by the potential. Let's say times PD. But let's say that in this case the PD is denoted with V. So it's V that we are going to find. Okay, then we feed in the formula here. The charge is already given as 2e, therefore we shall have 2e equal to 2e multiplied by the potential that we need is going to be equal to the kinetic energy, which is 65 kilo, that's times 10 to the power 3 electron volts. This is volt. Electron volts. Okay, then E is going to cancel out and then remain with the PDV, which we want as is going to be 65 times 10 to the power 3 divided by 2, and then this is going to give you 3.25 times 10 to the power 4 volts. So that's going to be the electric potential difference that can give a helium nucleus of charge 2e a kinetic energy of 65 kilo electron volts.